We start with a 3D vector class, the backbone of any ray tracer. It stores x, y, z coordinates and provides addition, subtraction, scalar multiplication, dot product, normalization, and a clamp method to keep colors between 0 and 1. Everything from positions to colors will be represented by vec3. A ray has an origin point and a direction vector, automatically normalized. A material holds a diffuse color and a reflectivity value between 0 and 1. Reflectivity 0 means fully matte, 1 means perfect mirror. Later, we'll use these to calculate shading. The sphere stores its center, radius, and material. The intersect method solves the quadratic equation for a ray-sphere intersection. It returns the smallest positive t, distance along the ray, or -1 if no hit. Optionally, it stores the hit point in hit point. This is the core geometric test. Light holds a position and color. The scene collects all spheres and lights, plus an ambient light level. Its intersect method loops over all spheres, finds the closest hit using the helper hit class, stores sphere, t, and hit point. If no sphere is hit, it returns null, meaning the ray escaped. The camera defines the view. Given a look from point, a look at target, a vertical field of view, and image dimensions, it computes an orthonormal basis, forward, right, up. GetRay converts pixel coordinates to world space rays. We flip the y-coordinate to go from bottom to top. Trace is the recursive heart. It stops at depth 5 to avoid infinite reflection loops. If the ray misses everything, we return a sky gradient, white at the top, blue at the bottom, blending by the y-component of the ray direction. Otherwise, we shade the hit point.
Inside trace after a hit, we retrieve the sphere, point, and normal. The ambient component is simply seen ambient times the material color. For each light, we cast a shadow ray from the hit point towards the light. If an object blocks it, shadow hit, t.
If the material's reflectivity is greater than 0, we compute the reflected ray direction using the formula reflect_r equals ray.d2 ray.d normal, ormal. We offset the origin slightly to avoid self-intersection. We recursively call trace with increased depth, mix the local color with the reflected color using the reflectivity weight, and finally clamp the result to 0,1. We build a small scene, a red sphere, a shiny blue sphere, a mirror sphere, a large green sphere for the ground, a yellow sphere. 2 lights, a bright white and a reddish fill light. The ambient is low, 0.1. This setup creates colorful reflections and shadows. We iterate over every pixel, generate a ray, trace it, and store the color. Progress is printed every 50 rows. Finally, we write the image as a ppm, plain text format, easy to view with many image viewers. The output is a 800 by 600 image showing the scene with realistic lighting. You've built a complete ray tracer from scratch. This one file covers vector math, geometric intersection, shadow rays, reflections, and image output. Understanding this gives you a solid foundation in computer graphics and the confidence to explore more advanced techniques like refraction or Monte Carlo sampling.